Yeah, I want, thank you very much. Thank you for this opportunity. I want to give kind of a general, it's more kind of a survey talk about some aspects, certainly not all aspects of high-dimensional expanders and a little bit on Ramanujan complexes, but I want to start with expanders, even though I'm pretty sure that everyone knows this material, because I want to put it in the context of, to put the high-dimensional expander in this context. So, okay, so let's just recall the definition. Expander X VE is a finite graph. We look at the so-called Shiger constant, which is the minimum over all the subsets of V, which are not neither the empty set nor V, of the number of edges from W to the complement of W divided by the minimum of W and its complement. Another way to say it, you can say I take the minimum over all subsets of V of size less than half, and I check how many edges are going out divided by the size of the set, and it's called Shiger constant because Shiger study this type of object in the context of Riemannian geometry. And we say that X is an epsilon expander if this Shiger constant of the graph is at least epsilon. Now this is and now by nowadays standard, this is an easy results which attributed to Pinsker, though later on it was found out that it was probably was discovered even earlier, but let me not get into that random k-regular graph are expanders. Because if you really think about it for a second, it's not at all clear that expander exists. Oh, sorry, what's going on here? No, you're not supposed to see this. Okay, let me use, okay, I will go slow, sorry. Okay, so this was the work of Pinsker and Margulis.
So before, Alex, just maybe you want to stress, so you want to say K is a constant and this.
Oh yeah, oh, I'm sorry, yes. What we are interested, I will indicate this in one of the paragraphs. In the applications, you usually what you want to do is K constant, and the size of the graphs is going to infinity. And then it's not so trivial that graphs like that exist even. But Pinsker proved that random K-regular graph are expander, and Margulis was the first one to give an explicit construction, and for that he used Kashdam property T. I don't want to go to explain what is Kashdam property T, even though it will be, it is a wonderful thing to know, but this will take us out of our main story of today. But I just want to say that Kashdam property T is something from representation theory. So Margulis suddenly put representation theory of groups, discrete group and semi-simple groups into the game for this combinatorial problem. And he proved that if gamma is a finitely generated group which has Kashdam property T, and there are plenty of groups which have this property, for example, SL3Z or SLNZ for n greater or equal 3, which is just the n by n matrices of determinant 1 over the integers, and then you look at all the finite quotients of gamma, you look at all the normal subgroup of gamma of finite index, you look at the finite quotient and you take Cayley graphs of them with respect, but be careful, with respect to the generators of gamma. You don't choose the generators independently for each one of them. You took the generators for gamma, you pull them down to gamma mod n, so you get generators for the finite quotient gamma mod n. You look at the Cayley graph and you get an infinite family. This is clearly a K regular for a fixed K, because K is equal to the size of S, or twice the size of S, because you have to put the inverses. And then you get an epsilon expander for some epsilon. This epsilon depends on in the Kashdan property. There is also an epsilon, so a different epsilon, but there is it depends on that epsilon. I don't want really to elaborate here on that, just to say that suddenly representation theory came into the game. Now there are various yeah.
Yeah, I mean, if people are not happy with arbitrary normal groups there, I mean, if you take the, I don't know, 3 by 3 matrices over the integers, then you can just take modulo n or modulo 0. So the quotients you take are just taking, instead of all integers modulo
m,
2,
and then
3,
you get
5,
SL3
10 million, and all of these guys will be expanders with the same generating set.
Right. In fact, Avi, here there is a deep theorem which is not needed, called the congruous subgroup property, which says that these are basically all the normal subgroups. So in fact, in this case, you don't really, this is not even a restriction. It's really the full set. And in SL2Z, it's a different story, but I don't want to get to that. Otherwise, we will not get to the main story. Okay, now some well-known results of starting with Tanner, Alon, Millman, Shiger in the geometric context showed that basically expansion is equivalent to spectral gaps. What is a spectral gap? This means that if you look at the adjacent symmetrics of the graph, so if the graph is as n vertices, and let's say it's a K-regular graph, then it's not difficult to see that the eigenvalues of, because it's symmetric matrix, all the eigenvalues are real, and they are all lies between K and minus K. K is always an eigenvalue, and minus K is an eigenvalue if and only if the graph is bipartite, and all the other eigenvalues, there are n altogether eigenvalue, maybe with some multiplicity, and they all in this interval. And it turns out that X is an epsilon expander if and only if the second largest eigenvalue, namely lambda 1, which is always strictly less than lambda 0 if the graph is connected, or let's even say if and only if the graph is connected, then lambda 1 is less than 0, but if it's bounded away from lambda 0, if it's bounded away from K along the family, then these are expanded. In fact, there is a good hint here, because you see the graph is connected if lambda 1 is less than lambda 0. If it's bounded away from lambda 0, then it is very connected, and very connected is exactly expander. The definition of expander, if you think about it, is a kind of a very much connected. Okay, so if you want to get better and better expanders, you want to bound lambda 1 as far as possible from K. In fact, it's a nice little exercise to see that these eigenvalues control the random walk on the graph. And so, and if they are small in absolute value, then the random walk would converge very quickly to the uniform distribution, and you cannot, and it's not difficult to imagine why this is an important property in algorithm computer science, and also in various mathematical contexts. Anyway, a well-known result of Alon and Bopana says that there is a limit of how much you can bound lambda 1 from lambda 0 if we are talking about an infinite family when K when n going to infinity. We fix k, we let n going to infinity, then the best you can opt for is that lambda will always be at least 2 square root of k minus 1 plus little o of 1. So the best you can opt that this will be the bound, and we will call a graph to be a Ramanujan graph if all the non-trivial eigenvalues are indeed bounded by this number. Okay, you must ask yourself where this number come from. I don't have time also for that. I just say that I just give an hint. The universal cover of the K regular graph is the infinite K regular tree. The K regular tree is an infinite object in some sense that can be made maybe somewhat precise. This infinite object is the ideal expander. That's the best graph in some sense. But we live in the real world, and we must work with a finite graph, so the eigenvalue k is kind of enforced on us. And minus k also if it's a bipartite, and in some way we want to say that all the other eigenvalues are just as good as in the infinite. Oh, sorry, I forgot to say the importance. Now, one can think about the infinite graph as the ideal expander. And in the infinite K-regular graph, if you take the adjacency operator acting on the L2 functions there, the spectrum is exactly the interval between minus 2 square root k minus 1 to 2 square root k minus 1. And we want that in our finite world, all the eigenvalues will be only those that in some sense coming from this infinite object and nothing new. Okay, that's kind of a way maybe to remember why this number is important. Anyway, the connection that was set up by Margulis between representation theory and combinatorics led in the 80s to the construction of Ramanujan graphs. So it's by no means a trivial statement. There is no easy proof to show that Ramanujan graphs exist at all. It's still an open problem about random graphs, if they're Ramanujan. Probably they are not. There is some conjecture that the positive proportion of them is Ramanujan, but all this is not known as of now. Anyway, explicit construction of Ramanujan graphs was made by Margulis and by Phillips and Sarnak and myself in the 80s, and they were constructed in a very fancy way, which again, I just hint without going to much details. The story is the following: you take F to be a local field. For example, F is the p-adic numbers, or F is the Laurent power series over the finite field of order P. This is a local field. It has a locally compact topology. If you look at the group PGL2F, these are the 2x2 invertible matrices of F divided by its center. You divide it by its maximal compact subgroup. Those of you who are familiar with such a story over the real number, this is like the analog of the hyperbolic 2 plane. If you take here the real number, you will get the hyperbolic plane. Here we get a p plus 1 regular tree, and now we take a arithmetic lattice of PGL2F. This is a co-compact discrete subgroup in PGL2F. And then we divide PGL2F first by K from the right, we get the P plus 1 tree. We divide it from the other side by a congruent subgroup. These are exactly the kind of group that Avi talked about before. You know, you take a congruent subgroup in such an arithmetic group, and you divide by it, then this is a tree divided by a group, so it's a graph. On the other hand, it's a co-compact here, which means that the quotient is compact. So this is compact and discrete and therefore finite. And this way, in this fancy way, we get some finite graphs, and these finite graphs are Ramanujan graphs. There is an essential number theory involved, because you see, what is the definition of Ramanujan? Is that lambda is less than 2 square root of k minus 1. In our case, I just told you that k is equal p plus 1. Now, p plus 1 minus 1 is p. So we have that all lambda are less than 2 square root p. 2 square root p should ring a bell. That's the number which we all know from Riemann hypothesis over finite fields. And in some way, this theorem or Riemann hypothesis of finite fields is really behind these results via the work of Ecke or Delin or Drinfeld. Again, this is just to get a little touch, because when we'll go to the upper dimension, to the higher dimension, it will give us hint where to look for high-dimensional objects. Anyway, very quick history. As I said, random k-regular graphs were proved by Pinsker. Margulis used Kashdam property T. Ramanujan graphs were constructed in the 80s by a few of us. Avi with Reingold and Vadam in 2002 came with a zigzag product, which is, I think, even up to now, the only elementary method which is known to get expanders, explicit construction of expanders. And it has many other applications. And more recently, Marcus Pillman and Srivastava got another way to get Ramanujan graph, and in particular expander, via the so-called interlacing polynomial. And the name of the game here is always, or almost always, that we want k-regular graph k fixed, epsilon greater than 0, and x goes to infinity. There are plenty of application. I'm not going to tell you. I mean, I guess so many of you know better than me. There are a long survey, one by Khoury and Nati, Lineal, and Avi, about expander graph and their applications. These applications are mainly not only toward computer science, and I also wrote such a survey, and in my survey is that I talk about various applications, or mainly to pure mathematics. There is the main application which was really done here at the Institute is a sieve method, and some application to wonderful kind of a non-commutative number theory. So anyway, these days, expanders are all over the place. If you eat expanders in the, if you write expanders in Google, then you get 4 million mentioning of them, but don't get so excited, because most of them talks about this type of expanders. And this should give us at least a little bit modesty to understand our importance for society, because I think more people are interested in this type of expanders rather than other type of expanders. Anyway, I want to talk only about one application of expander, and I do it with a reason, because I want to present you some thinking and open problems which will give you a good motivation to think about high-dimensional expander to problems in coding theory, a problem that one-dimensional expanders cannot solve. So it's kind of frustrating that I don't hear anybody there, but it's fine. You hear me and I can continue, right?
We hear you. Somebody asked whether you can go into presentation mode of your PDF, but I'm not sure.
If I can do what?
Well, I think, well, anyway, your slides are visible. It doesn't matter. Forget it.
I can send them after that if you want me to.
Okay. Yeah, no. Anyway, go on. I think we can hear you, and people know that in the seminar you are free to just stop Alex and ask him whatever you want.
Yeah, please. The other way around, like I talk and and also because I put the screen in front of mine, I don't see you, so I'm even not sure if you are still there. Okay. So let me give a quick application, a very famous application to coding theory, to error correcting codes. And I want to stress something that even people who know about that will see some connection toward the end of my talk. So let NKD be a code. So this is basically just a subspace. I'm talking only on linear code of f2 to the x, where x is of size n. This is the so-called the length of the code. This is a subspace of dimension k, and the distance is d, which means this is the minimum of the weight of the vector, the Hamming weight of a non-zero vector in C. Right? This is the classical NKD codes. And we know that using such an NKD code, we can send k bits. Instead of sending k bits, we send n bits. And we want the distance will be d, which will enable us to correct d over 2 mistakes. Now, the rate of the code is k over n. The normalized distance of the code is d over n. And the classical notation or names, so going back to Shannon, that good codes are code, or asymptotically good codes is a family of codes when n goes to infinity, the rate and the distance are both bounded away from 0. So Shannon proved by random method that such code exists, and ever since then it was a problem to find good codes with this explicit construction, and sometimes with other properties which are needed in real life. For example, let's talk about the following. Given a code C, let's denote C perp. C perp will be all the vectors in X which are orthogonal to the code, orthogonal in the mode 2 product, right? W times V is equal to 0 for every V in C. So the usual kind of inner product, scalar product over the finite field of order 2. And now the dual code C perp, we can think of it as the code by itself, but that's not really what we want to do. We want to think of it as the space of constraints. These are, we think of every element of C perp as a linear functional on the space, and C is the kernel of all these, is the common kernel of all these linear functional. In fact, C is the perp of the perp. Now, the code C, again, when I say code, but I always mean a family of codes when n goes to infinity, is called LDPC, low density parity check, if there exists a set of defining constraints. So if we have a basis for C perp, which contains vector of bounded weight. Now you can imagine why this is of importance, because I am the receiver. I'm getting a very long word, and I want to check if this word is really in the code. I have to check if it passes all the equations. I want the equations to be as short, very short, otherwise it will take awfully a lot of time. And Gallagher, long ago suggested this notion of LDPC, and he proved along the same lines of Shannon that LDPC code exists by random consideration. If Shannon proved that if you pick up random constraints, the set of solution as a good distance, Gallagher said if you pick up random constraints of bounded Hamming weight, the set of solution is also fine for coding, so they exist. But it was a long-standing open problem. How to make explicit construction of such LDPC code, and the famous work of Sipser and Spielman did it. Let me give you the construction. It's actually fairly easy. It's actually quite amazing. It's so easy in some sense. On the other hand, it was really a revolution in the area. When Spielman got the Nevalina Prize, then the committee really stated this work of him as one of three major pieces. But as you can see, I basically will give you with almost not complete proof in 2 or 3 slides.
Alex, Tanner already used expanders to construct explicit codes. They did much more, Sipser and Spielman, and also Spielman in his work on linear time encoding and decoding. But anyway, yeah.
Really? You mean
Tanner in 1980 had explicit. He used expanders to define codes, and in a similar way. They did more. But
he proved that LDPC and all this.
Well, it's a regular. It's a constant degree expander. It's a similar, yeah.
I didn't know that. Okay.
Yeah, but anyway, yeah.
Yeah, they also do the coding, linear time, etc. Which is also not very difficult. I mean, it was really. Kind of revolution.
The linear time is difficult, but close to linear time is
not so difficult. I mean, okay. I mean, it's.
No,
I think I once even taught it in an undergraduate class. I mean,
not the decoding, Alex. The encoding. The encoding is far from obvious. It's a linear transformation, so the obvious thing is n squared, and yeah, it's not. I mean, Spielman code which you can encode in linear time is far from obvious, and it's
coding. I see.
It's not the description you are given. Yeah, decoding is easy. Okay, but go ahead.
I see. Okay, I didn't know. Okay, I didn't know that aspect. Okay, that's not in the original paper.
The encoding is just so linear time encoding and decoding in this separate paper of Spielman. That is in the fellow paper. It's not in the Sipser Spielman paper.
I see. Okay, this I didn't know. Okay, thank you. Okay, let X again be a K-regular graph, but now you'll see in a minute why I want the number of vertices of V to be M, not N, and the number of edges in this case, this will be over N is M times K over 2. Now, we are going to define a code of length N, this is N, using a small code. The small code will be, again, it's just a subspace of F2 to the K. Remember, K is constant for us. This is a small code once for all that will be chosen in a minute. And then we'll define the large code on E. Now, E will go to infinity, the size of E, because M will go to infinity. And then now we are getting a family of codes. All of them are defined using a fixed small code. This will be the following. We look at all the functions on the edges of the graph. You see functions from E to F2. So this is like putting on the edges of the graph zeros and ones. But the full space will be of dimension n, which is the size of E, but the code is going to be a subspace. What will be the subspace? The subspace will be the following. For every vertex of V, we look at F localized at V. Just think about yourself. You sit on a vertex V and you look around yourself. When you look around yourself, you see K bits. And the K bits are organized in some way. It doesn't matter. Put numbers on the edges around every vertex, just 1 up to K, and it doesn't matter how, and we are not requiring any consistency. So the same edge on one side might get some number I, on the other side it will be number J, and this is fine. Just do it once, and then look at all the functions that if you look the local view from V of F is in what is not G, sorry, it's in B. I'm sorry, not G here. The little G should be B. You see, you look at all those functions on the which define globally, but you want that locally they are inside the small code, the fixed small code B. This will be called CXB. And then Sipler and Spinman proved that this is a linear code. This is trivial to see that it's linear code. The N is MK over 2. That's also trivial. The rate is at least twice the rate of B minus 1. This is also trivial. You just count the number of equations, you see. You count the number of equations which define B inside F2K, and you have to multiply it by the number of vertices. What is slightly less trivial, but it follows from some basic properties of expanders. A nice way to present it is via some results of Alon and Noga Alon and Fan Chang, that the rate, the distance of the large code is bounded by this interesting number. The number is interesting because you see I connect here delta of B, it's the distance, the normalized distance of the little code B, which is a number between 1 to K, minus lambda 1, which is also a number between 0 to K, and this is also a number between 0 to K. If this is bigger than this one, it should be bigger. I'm sorry, not even though I take square, it should be really bigger. Otherwise, there is no. It's not true. Then we get an expander. Anyway, if we will choose B good enough to win to over lambda 1, because of the Ramanujan graphs, if you want, lambda 1 can be very, very small, much smaller than K, then there is no problem to find such a B, and then you get LDPC graph. And here is the explicit corollary. If the rate of the code is more than half and delta of B is more than lambda, we get LDPC code, etc. We'll get back at the very end of the talk. We'll get back to that, and it will be relevant for us for other things. But the time is running, so let me go to the higher dimensional story, which is the main story. And all up to now, all this was kind of motivation, but it was more than motivation. It kind of, some of it will points us the direction where to go when we go to high dimensional theory. So first of all, when we say high dimensional theory, we can talk either about hypergraphs or about simplicial complexes. And basically it's the same thing. My experience, it depends on your background. If your background is a computer science, you say hypergraph. if your background is in math department, you say simplicial complexes, but because we go to uniform hypergraph and pure simplicial complexes are basically the same. So let me just define, if V is a finite set, a D plus 1 uniform hypergraph is a collection of subsets of V, all of them of size D plus 1. And a D-dimensional pure simplicial complex is a collection of subsets, faces of V, which is closed under inclusion, and all the maximal one are of size D plus 1. So basically, when you think about simplicial complex, you say, I don't take only the top ones, but I really think about all their subsets. But of course, you can pass from such a, this is called pure if all the maximal ones are of size D plus 1. You can pass from a pure simplicial complex to a uniform hypergraph and vice versa. And so this is just basic, it is just a question of language. And it's kind of interesting that it's easy, you know, the notion of Ramanujan graphs is in some sense more complicated than and less trivial somehow, even as a definition, than the notion of expanders. But it was kind of easier for us to guess what should be higher dimensional Ramanujan graph before we really started to get a feeling what should be high dimensional expander. To be honest, even now we are not sure what high dimensional expander. I will show you a few possibilities. So a theory of Ramanujan complexes has been developed something like 10, 15 years ago. Winnie Lee and Beth Samuel, Uzi Vishna and I, and Angie, we all more or less at the same time started to build such a theory. And in a minute, you will understand why, and why suddenly we all started to work on that, because what you remember that the Ramanujan graph that I presented before were obtained by looking at PGL2 of a local field F, taking the associated tree called Boatitz tree, dividing it by some congruent subgroup, and we got graph. There is an higher dimensional theory. If you take PGL D plus 1 of F, then you can and you divide it by its maximal compact subgroup, you get the so-called Boatitz building. Boatitz building are infinite, contractible simplicial complexes. So the case of dimension D, so if D plus 1 equal 2, D equal 1, we get infinite contractible space of dimension 1, namely a tree, and that's the P plus 1 regular tree that I talk about. So these are kind of an higher dimensional versions of trees. And if we divide them by action of congruent subgroup, we get some finite simplicial complexes. Now you can generalize the Alom-Bopana to this context, talking about some optimality of spectral gap, and then you can use the work of Laforgue. Then I have to say a few words about that. I told you before that the construction of Ramanujan graph was based on the work of Delin in characteristic 0 or Drinfeld in characteristic P, and the so-called Ramanujan conjecture for PGL2. This work was extended by Laforgue, Laurent Laforgue, for PGL-D, for every D, D plus 1F, only in characteristic P. It's still an open in characteristic 0. And whatever it means in representation theory, we wanted to understand the combinatorial meaning of his work. So the combinatorial, just like the Ramanujan conjecture for PGL2 which is a big theorem in representation theory, turns out to have a down-to-earth application to discrete mathematics, to finite objects like graphs, we said, okay, there must be some meaning to his work on some finite simplicial complex, and we work them out, what is the meaning, etc. It's a bit too long and too technical to give the full story, and in fact, for example, the paper of mine with Bet Samuel and Uzi Vishna already published in 2005, and to be honest, for few years, nobody paid attention to it, because, and it's clear why, because we didn't have any application in mind. You know, we just had the feeling that there must be some beautiful combinatorics behind this theorem, and we worked it out. What are the objects? We even have explicit construction. Everything is much more difficult. It took us a long time, but eventually we did all of this. And now, if you want to see explicit construction of Ramanujan complex real, then you have to go to India, and then in West Bengal, there are explicit construction of Ramanujan complexes. Okay, so in a way we understand what it means to be a Ramanujan complex, but what does it mean to be an I-dimensional expander? So in short, I would say that, that the answer we don't know. But there are several approaches. I will bring today only maybe two, which are not the most natural, I admit. You see, the most natural would be maybe to say, let's try to think about expansion in the basic property, like you remember the first definition I gave, and some people worked out such a definition in I-dimensional, you know, kind of expanding. And another one is about spectral gap, but spectral gap of what? You see, in the one-dimensional, there is one operator, a natural operator, the operator of summing up around the vertex, around the edges, around every vertex. The adjacency matrix is kind of a natural. It's one operator which give you the full information about the structure of the graph. What does it mean, spectral gap in the I-dimensional? Now, there are answers here, but I will not talk about today, but I will use this opportunity to make a little advertisement for a talk that will be given tomorrow by Zar Oppenheim in my stability seminar here at the Institute at 11. He will talk completely accidentally. We didn't plan it to be with my talk, but somehow he will give a self-contained lecture about Garland theory. Garland theory was developed by Garland like 40 years ago to solve some conjecture of Serre about cohomology of some quotient of building, but in the last few years it was found that it has that you can really think about it without p-adics, without buildings, just as a very down-to-earth combinatorial theorem about Laplacians and eigenvalues of simplicial complexes, and it turns out to have a good number of combinatorial applications. So Zar Oppenheim will talk about this, and then you can see another approach to I-dimensional expander. So I will not talk about that, though this is a very interesting direction. I'm going to take an amazing, at least in my point of view, and completely unexpected a kind of thinking about I-dimensional expanders, which is due to Gromov. And it's very, it's kind of, you look at that and you say, wow, only Gromov can come up with something like that. But the story actually starts much earlier. So even if you lost me, I will start now. I'm starting now, in a way, a new lecture. And the new lecture goes also just like the Ramanujan graph and the expander go back quite a while ago. And it starts with the following lovely, beautiful theorem of Borosh and Furedi. Borosh and Furedi, I believe, are now quite well-known mathematicians, computer scientists, but at that time there were 2 undergraduates in Hungary who proved the following theorem as an answer to a problem which was posed by Erdos. And it says the following very simple, beautiful statement. It says the following: giving a set P in the plane with n points, now draw all the triangles on that endpoint, right? There are, once you have n points, you can draw and choose 3 triangles. Then there exists Z in R2, which is covered by 2/9 of them. 2/9 of the triangle doesn't matter what are the points, how you put them, a linear function of them, even an explicit number, 2/9 of them will meet. There is a point which is covered by 2/9 of these n choose 3 triangles. A very beautiful, nice theorem. Now there are a number of proofs for that. Some of them are short, even fairly short. And it was proved later on that this 2/9 is optimal. Okay, shortly after that, Barani came up with a higher dimensional generalization. So let's read the theorem of Barani, which is shortly after that.
Alex,
yeah.
maybe before the generalization, you want to say a specialization. So if we were not talking about the plane, but rather about the line, the one-dimensional case, then it would be a triviality, right? Any way you put n points on a line, and you draw all the segments, which are n choose 2, there's always a point which is covered by a constant fraction of them, roughly half.
Right.
So this
actually, you're right. Thank you very much, Avi, because you helped me to explain in a minute the connection with expander. I mean, even your remark is very easy, elementary. It's a very important one, because we will come back to that in a few minutes.
I know, that was my purpose. Okay.
Oh, I see. I thought you were smart. You just know, okay. Okay, thank you. So fix D now. Then Barani Theorem says that there exists some constant, a positive constant, such that for every set P in R to the D of size n, there exists a point in R to the D which is covered by at least this linear proportion of the n choose D plus 1 D simplices determined by P, right? If we take n points in R to the D, every D plus 1 point that determine uniquely a D simplex, then we get n choose D plus 1 simplices, a positive proportion of them, again independent of n and independent of the location of the point, do intersect. Gomo now generalize this, give a strong form for these theorems, and which is kind of amazing. But before we give Gomo theorem, let me give you a definition, because Gomo changed also the point of view of the way we think about these theorems. We think about, when you see this theorem, you think about it as a property of the Euclidean space of R to the D. Gromov taught us to think about this theorem as a theorem about simplicial complexes, or about hypergraph, whatever you prefer. So let's say that let X be a d-dimensional pure simplicial complex. I always work with them. We say that X is the geometric, in a minute we'll talk also about, respectively, the topological epsilon overlapping property if for every map F from the x0 are the vertices of X, we take any map from x0 to R to the D, and then we take an affine extension. There is essentially unique affine extension from the simplicial complex to R to the D, because you see, you have the points, you have lines between them, so you extend F to the straight line between these points, and then you get triangles, and then you get pyramids, so you have an affine extension, a unique affine extension, F tilde. Then there exists a point Z in R to the D, which is covered by epsilon fraction of the images of the top dimensional faces. Namely, the D-dimensional faces are a positive proportion of them, epsilon a fraction of them cover the same point. So if you think about it for a second, Barani theorem means that if you look at the complete d-dimensional complex, namely you take n points, you take all the d+1 subsets of it as the d faces, then the theorem of Barani tells you that they have the geometric epsilon overlapping property. That's exactly the theorem of Barani in this language. But Gromov defined also not just the geometric epsilon overlapping property, but also the topological. The topological means that instead of taking, you start with F from the points to R to the D, but now I allow you to take F tilde to be any continuous extension of F. Not just F1. F1, there is essentially unique one. F tilde continuous, there is awfully a lot, uncountably many. You know, you can make it in a completely crazy way. You make the extension. Okay, and then we say that the complex has this topological overlapping property if for every extension, for every continuous extension, there exists a point which is covered by epsilon fraction. And he proved the following amazing theorem. It's really amazing. He proved that if you take the complete complex, namely you take all the C, and you take n points, you let n go to infinity, d fixed, you take all the d+1 cells, all of them, it has also the topological overlapping property with some constant CD. The amazing in his theorem, you know, he proved with a constant CD which was better than what was known before for the affine case by the Barani theorem. And it's so much stronger theorem that, and if you think about it for a second, it looks like it's impossible to be true. We are among friends, even though you record it. I have to say that when I saw this for the first time, I didn't believe it's true because it looks like it cannot be true. And let me illustrate now with a movie. Do you see the movie? Do you see the movie?
Yes.
Yeah.
Okay, so this is a little movie which illustrates Gromov theorem. So we have here, we start with only 8 points. Okay, so of course 8 is not enough, but because 8 choose 3, what is it? Is I think 56. So this is Barani theorem. Barani theorem in the plane, well, that's the Borsch-Foredi. You know, you start to put all the possible all the possible triangles, and then you see you get an area which is heavily covered by triangles, and okay, and the theorem tells you that even if you continue to do it with many more points and many more that, there will be some area, some point which is covered. But think what Gomo theorem tells you. Gomo theorem tells you that you can make the map as in any way you want. The meaning is that I do now triangles, but not by straight line. I do it in any way we want. I can avoid completely. Let's say that I know the area, this little purple area in the previous picture, which was covered by them. I can completely avoid it. I can make the triangles completely bypass it and go around and not at all touch that area. Then Gomo tell you it won't help you. You see, you will meet somewhere in a different place. You see this green which come up here. You see it's completely outside the purple, but you still have this area. And in fact, he proved it in dimension 2 with the same constant 2/9, which was the optimal. And as I told you, he proved it with the constant 4D, which was better than was done before. By the way, it's still a major open problem. What is the rate of decay of CD? By the way, okay, the flags from Brazil and Israel, because I prepared this. Well, I didn't prepare it. Somebody prepared it for me for the talk at the ICM in Brazil 2 years ago, and then I wanted to be nice to the local people, so I put the flag of Brazil and my flag. Anyway, so this, yeah.
I have a question. Do you know that the topological expansion equal to affine expansion, or we don't know this fact?
No, I know that they are not equivalent. In fact, I will say a few words about that in a few minutes. If I forget, then tell me two of them, because the difference between them is something which caused me to think, and I want to speculate about some conjecture that I will tell you something after that. I don't want to stop now, but they are not. I don't think they are equivalent. No, moreover, I know they are not equivalent. I will give you an example.
Okay, thank you.
Okay, just a second. Okay, so let's continue. So what all this has to do, this is a very beautiful story, but what this has to do with expander, why we brought it here? The reason we brought it here is that this is really a generalization of the concept of expander. And here I want to use Avi's remark. Look at the case D equal 1. And assume you start with a graph X, which is just vertices and edges, and assume that this is an epsilon expander. Now let's see what does it have the overlapping property, the topological or the geometric overlapping property. Well, what we have to do, it's very trivially, right? We have to take a map from the vertices x0 to the real numbers, and then we claim that there exists a point in R such that half of the images are below it and half are above it. Why? Of course, this is true for the complete graph, but why this is true also for an expander? That's not oh, sorry. There exists a point. Sorry, the next line. Yeah. I'm sorry. This line is still true always. Yeah, there is always up point before and up the out. This divides the graph into two sets. Let A be the vertices whose image is below Z, and so A bar, the complement, is above. And now all the edges from A to A bar, when we take any continuous extension of F to the graph, must pass this point. So if this is epsilon expander, it means that many edges are going through that point, and we get the topological overlapping property in a kind of a trivial way. And it's not, if you think about it for a second, you see that this is not a property of every graph. This is really a property of expander, though it's slightly less, it's slightly weaker than expander. If you really think about that, it's possible that the X will not be connected. Assume X is a union of a huge expander and a small graph, which it doesn't matter what it is, then it still have this property without being formally expander. It basically says that, you know, if you cut it like that, many edges. Okay, so let's give a name. Let's give a name, and we say that a family of d-dimensional simplicial complex is a family of geometric expanders if all they have the epsilon geometric overlapping property, and we will say that these are topological expanders if they have the epsilon topological overlapping property. And you see that this is a generalization of expander. Maybe this is a good time to take a break. When should we take a break?
Whenever you want. So if this is a good time for you, then it's a good time. So we can take a
maybe I think it's a fairly good time, and now you can kind of digest this concept, and then we will continue.
Okay, excellent. So 5-minute break.
Okay, good.
Alex, can you explain again what's the difference between geometric and topological expander?
Yeah, in geometric expanders, you say you take the simplicial complex, you take a map from the vertices, and you require this overlapping property just for the affine map. You extend.
So it's affine and topological. I see.
Right, and in the topological, you want the property with the same constant for every n, for every location of the points, and for every continuous extension. And there are so many continuous extensions. As I try to illustrate in my movie, you know, you can go and do some crazy thing. You know, you can make I tell you, I wasted a lot of colors when I read Gomo, because I was sure that it cannot be true. And you know, sometimes, let's be honest, with Gomo, you know, he's not so careful about writing. And that paper, which is a great paper, an unbelievable paper, is even bad by Gomo standards, because it's clear when you look at it that it was not even proofread, and there are so many typos and etc. But anyway, you see, because you can kind of escape. You can make the triangles to be very, very, very narrow, and why they should meet each other. I'll give you an hint. Eventually, they meet each other because just think about dimension 2. You have endpoints, and then you put a line between vertex x and vertex y. This line, you cannot move it anymore. Yeah. You see, once you put the line, you can put it in any way you want. But now on this line, you have like n-2 triangles lying on it, right? If you want all of them to be very narrow, you should all bring of them to be very close to that line.
Yeah, and this is hard.
Right, so you see, so eventually, if you try to bring them to be very narrow, you kind of push them to some corner, and then Gomo tell you, okay, so in that corner, there will be a point that's covered by many of them. This is kind of the amazing phenomenon.
Is there an easy proof of Gromov today?
I wouldn't say, no, I don't know any easy proof. The only proof is cohomological, but there is a beautiful exposition which almost basically avoid the language of cohomologies, F2 cohomology, which I maybe will try, if I have time, I will try to explain what's the point there. By Amir Yudayov. I don't know if Amir is with us. He usually comes to this seminar. Amir, are you here?
No, don't see him.
He's not here today. Yeah, he probably knows this material very well. So Amir wrote, I don't know if it was published, but he wrote a beautiful, like something short, this maybe a few pages, explanation of that proof just in dimension 2.
Oh, right. So in dimension 2, you can like write it in 2 pages?
No, not, I didn't say 2, I say few. Maybe 10 pages, something like that. I mean, but he kind of, I think he almost, yeah, maybe avoid the language of cohomology. I mean, cohomology over F2 is not something too complicated, but still something people are frightened by this. I mean, I don't know if he really published it. Maybe it was published somewhere. Anyway, I should have it somewhere. If you drop me an email after that, I will find and I can send you. But Amir probably can give you.
Wait, I have a question. So does his proofs go for topological expansion, from cohomological expansion?
No, for topological. No. Yeah, for geometric expansion, you have by now many proofs which are not many, several proofs, and some of them are. There is a published proof there, I think, of 2 pages even.
Shai ever send just a paper, a link to the Amir's paper?
What?
I'm saying, like in the chat, Shai sent the link to the Shai ever.
Yeah, I put the link
to the paper of Amir.
Yeah,
yes,
and it was published, by the way.
It was published. Very nice. I didn't see it. You send it by what? By the Zoom? By the chat? I don't know how to find the chat now when I'm sharing. I'm afraid.
We will send you the paper if you don't have it, Alex.
No. I have a preprint of it long ago. I even once taught it in my class. I mean, it's so good that it was much better than
anyway, so let's see. Everybody's back. Yeah, there's how to get an answer. So, Alex, you're ready?
Yeah, I'm ready.
Okay, so continue.
Okay, so yeah. Okay, now, but let me see what we saw so far. So far, we saw that the complete simplicial complex of dimension D on n points and going to infinity is a geometric expanders by Barani, and it's even a topological expanders by Gomo, and this is an highly non-trivial theorem. But if we go back to dimension 1 to prove that the complete graph is an expander is a triviality, right? This is not even high school; it's elementary school exercise, right? So Gromov, you remember I gave you the history of this. So there is a random Kashdam property, Ramanujan, zigzag, interlacing. The goal of all this construction of expander graph is to get bounded degree. This is the name of the game, not to get to prove that the complete graph is an expander. And then Gomo put forward the following basic question: are there bounded degree geometric or topological expander? And this is not at all clear. In fact, I talked with Gomo, and he told me at the time that he was not sure about topological. He was sure about geometric, and he did something I will tell you in a minute, but he was not sure if topological expanders do exist at all. In the break, I talked with some of you, and I told you I played a lot with this game in dimension 2, and really play. And you see the game. As I said, you can make the triangles going a kind of being very, very narrow and kind of escaping any domain you want to escape, and you go to a very narrow depth. And somehow, why the theorem is true, still true, because once you put a line between two vertices x and y, and let's say that you want that all the n minus 2 triangles lying on that x and y, they all, if you want all of them to be very narrow, all of them should be very, very close to the line you already put between x to y. You cannot change the line anymore. So you must push them to that area. So somehow you start to feel that you escape to some corner, you push everything there, but then the point Z will be over there. But if you have only a bounded number of triangles, maybe you can escape, and maybe you can arrange such a game that you will never have too many triangles intersecting each other. That was the basic. Can I
ask a question?
Sure, sure.
When you say bounded degree, you mean vertex degree, or is it a degree of some higher dimensional cells?
Oh, okay. Wonderful, wonderful questions. You can ask the question in both forms. When people say bounded degree about simplicial complex, sometimes they mean that only the top. You take codimension 1 cell, and every codimension 1 cell is inside a bounded number of d-dimensional, and this sometimes we call bounded upper degree. I really talk here about total bounded degree, namely that every vertex is inside a bounded number of cells. If you talk about upper bounded degree, then the answer is not trivial, but much easier. If I have time, I'll say something. It's especially important in the case of random. So if I will forget, please remind me, and I say something when I'll get back to random simplicial complexes. But now I'm asking about the real problem. The difficult problem is about total bounded degree, that every vertex is inside. Yeah, thank you very much for asking this, because it gave me an opportunity to make this distinction. Okay, shortly after that paper of Gomo appeared in 2010, another paper, this time of Jacob Fox, Gomo, Laforgue. Now, we heard the name of Laforgue before, but this is not the same Laforgue. This time, this is his brother, Vincent Laforgue. Asaf Naor and Janusz Pach published the following paper, and they proved that for FDV, there exists bounded degree, bounded really in the strict sense, every vertex is contained in a bounded number of simplicial complexes of dimension D with the geometric overlapping. Namely, there exists bounded degree geometric expanders. And they gave 2 proofs. One is random. They made the construction of random simplicial complex, bounded simplicial complex. How? That's not difficult to imagine what is a natural. Think about how do you get bounded degree random graphs. Let's say K. Let's say that K is maybe. Let's say you want to get a K regular graph, random regular graph on n vertices. You take n to be very large. Let's say n is even. You divide it into K over 2 random subsets of size 2. And then you put edges in for every such set. You put an edge. then you do it again in a random way, independently of the previous one. Then you do it again, then you do it again, you do it k times, you get a random k regular graph. You can do the same thing.
We call it, each one of these we call a perfect matching. So you take the union of
union of k perfect matchings. Right, I forgot the word. Yeah, thank you. Right. Now you can do exactly the same thing in dimension 2 or in dimension d. Let's say 2, you take n, this time say divided by 3, or in the general case divided by d plus 1. You divide it in a random way to subsets of size 3, and you declare every such subset to be a 2-cell, and then you do it again and again and again. You do it some fixed number of times, k time, and you get a random 2-dimensional cells of bounded degree. And they prove that this graph of bounded degree are geometric expanders. But now, let me stop here, because I'm afraid that I will forget to answer the 2 questions that I had before. These random complexes are not topological expanders. So this gives answer to the question: are there geometric which are not topological?
Oh, you can prove it they are not. So you can prove.
Yeah, let me convince you. Let me convince you. It's not difficult to convince. I don't know if it's written anywhere, because in a way it's a bit too simple. There is no justification to write, and for some reason they didn't say it. I'm sure they were aware of that, but you see, think about the dimension 2 case. Okay, you have n vertices, and you have you divide it into triples, k time, but k is finite, it's bounded, right? And n is very large. The probability that x and y will appear in a triple more than once is basically 0, right? X and y, 2 vertices, will not appear twice in a triangle. So it means that you are getting such a simplicial complex such that on every edge you have only one, on every edge you have only one triangle. So this is kind of, if you think about it, this such of a complex is essentially kind of homotopically equivalent to a graph. You can really think of it as a graph that you put on the edges triangles. And then you can take a map, and then you can take this triangle to be very, very narrow. You take a map from a graph to the plane, a continuous map. Now we know that every graph, especially if the graph is expander, and this undoubtedly will be an expander, has a lot of intersection. There is an old theorem like that, I forgot, Valiant, I think, and somebody else. But there is not necessarily at one point which is covered by a lot of vertices. In fact, the other way around. You see, if you take a graph, even if you take the complete graph, if you take an expander and you take a map of it to R2, it's not planary. There are many intersections, but you can move the map to the graph in such a way that every intersection is a simple intersection, is an intersection only of 2 points. So you see.
Do you have a characterization of all high-dimensional expanders where geometrical and the topological expansion is the same or almost the same?
No. We know very little. No, I don't know. No, I see. We don't really understand. Basically, all what I know, I will tell you today.
Okay.
I haven't tell you yet all I know, but I will tell you. I mean, we know very little about it. But suddenly, and that's what I have to say, I got excited. Suddenly, in 2013, you know, after like 8 years that nobody paid attention to our paper, they suddenly said and come and said, oh, those Ramanujan complexes are geometric expanders. They have the geometric overlapping property. This is not so surprising in some sense if you think about that, because what are expanders? Expanders are mimicking random graphs, right? Ramanujan graphs are best expander. Ramanujan complexes, in a way, are supposed to mimic random. So, okay, you have to prove it. It's not so trivial, but the known properties of Ramanujan complexes are enough, and they prove that they are that. And suddenly, a connection was opened up between these two, these two areas. But they left open the more difficult questions, right? What are with bounded? Are there bounded degree topological expanders? Are there bounded degree topological expander? And as I told you at that time, Gomo told me that is not true. But of course, if the Ramanujan complexes are geometric expander, we must try at least, right? To prove and to check if they are topological expanders. This turns out to be very, very, very complicated, at least for us. There is some simplification now. And let me jump right away to the answer. This appears in two papers. The first paper did only the case D equal 2. And this was done by Tali Kaufman, David Kashdan, and me in 2016. It was published later, I'm not sure. And then it was extended by Shai Evra. I think Shai is here with us. And Tali Kaufman in 2017, but I don't know, it should appear in the journal of the AMS, right, Shai? I mean, but I haven't seen it yet. It's appear. I'm not sure it's appear or not. Anyway, it is on the archive. But look at the following very, very, very strange formulation of the theorem. The theorem says the following: we fix P to be very large. Oh, I forgot to say that. This was my mistake. Also, the proof here, I was too short. The proof of Fox, Gromov, and Laforgue, and Naor and Pach for Ramanujan complexes are geometric expanders. They didn't prove that all Ramanujan complexes in dimension D are there. They said, take P large enough. And now listen carefully to me, because that point is going to be important soon when we'll go back to error correcting codes. Look at fix P. Let P very large, but fix P. Now, if you take the Boatitz building for a given phi is an infinite bounded degree simplicial complex. So if you divide it by many different congruence subgroups, you get infinitely many simplicial complexes of bounded degree. Provided, I want to stress, you have to fix P. So they say, take very large P, but fix it then. You need very large P because you need very strong bounds on the eigenvalues somehow. So here we say exactly the same thing, but it's still very strange.
So Alex, you may want to say what's the degree of this Ramanujan complex if you fix P.
I'm a little bit ashamed because you have to take P to be extremely large for the theorem.
I think to calculate P, right? For every P in dimension, the degree is about
of a P to the D square to the power of D square.
Okay, but anyway, it's a constant depending on P and on the dimension.
Right, the constant depending on P and the D. Right, yes, that's true. So now, if you take, now you have to take P very, 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 very large. I mean, it's kind of an embarrassing if you really want to know how large you have to take, even for D equal 2, if we'll do the estimates, we have to take P to be maybe 10 to the 100 or something like that. Maybe when Shai generalized and simplified the larger proof, I don't know if he estimated the P, it's explicit, and you can, in principle, it's explicit. You can say how far you have to go, but it's still very large number. But you fix P, and then, but look at the following strange formulation of the theorem. Let X be a D plus 1 dimensional Ramanujan complex, not D dimensional. You take D plus 1 Ramanujan complex. And let's Y be its D skeleton. We take the D plus 1 dimensional. So when we work in we wanted to solve the case of D equal 2, we look at 3-dimensional Ramanujan complexes, which obtain from the group PGL4 over the periodic numbers. And you take Y to be its D skeleton. Namely, you throw away the top faces. It's kind of strange.
But it makes complete sense, right?
What?
It makes complete sense with what you explained with small lines, right? Because you want that every line will be incident to several complexes. So this way you force it, right?
No. But you see but you see, if I do that in dimension 4, I'm getting 3. If I do that, sorry, am I doing it in PGL4? I start with 2-dimensional. With 3-dimensional, I throw them out. I get in dimension 2. Why the Y skeleton? Why the D skeleton of a D plus 1 Ramanujan graph is better than D-dimensional Ramanujan? Why the D skeleton of a D plus 1 dimensional Ramanujan complex is better than D-dimensional Ramanujan complex? I don't know. I have no idea. And in fact, I don't know what's the right answer. It's only the method of proof which causes. If I have time, I will say a few words about that. It's only the method of proof that somehow took us to this strange formulation. We don't really understand, and I don't think it's really true. Okay, let me just finish the sentence. The sentence says that this is a topological expander. Namely, we fix P, there exists some epsilon depending on P, depending on D, such that for all D plus 1 dimensional Ramanujan complexes, the D skeleton of them, namely, I throw away the D plus 1 faces, I am left with the D-dimensional simplicial complex. These D-dimensional simplicial complexes, or if you want, uniform hypergraph, they are topological, epsilon topological expander to some epsilon depending only on this P. And I don't know what's the answer. I really don't know if the full Ramanujan complexes are a topological expander, because the work of Shai and Tali solved the problem for every D. Then this is a complete solution to Gomo theorem. But it still leaves us unhappy, because it would be so much natural to say that the Ramanujan complexes are expander, but we don't know that. Okay, now I want to move. I still want to say something about local testability, and now go back to a little bit of the computer science connection. I hesitate even to say application. There are some applications now, but what it has to do with codes and with some computer science application.
But before that, Alex, I mean the theorems that you know, Shai and Tali and your previous theorem say that these Ramanujan complexes or whatever their skeleton are topological expanders. You define topological expanders using topology.
Right.
And continuous maps. You define Ramanujan complexes using heavy algebra. You have to say something about the connection.
I don't understand the connection. I know.
I mean, at least I don't. Well, I mean, there is a proof there, right? I mean, there is a criterion, an algebraic criterion. That
that's I will say. That's I will say.
Okay.
That's if I left time, I will say. Right. You are. That's I will say. But we can. There is a criterion using cohomology due to Gomo. And we can prove this criterion. Well, in fact, the criterion as stated by Gomo is not true for Ramanujan complexes. It's true for the complete, it's not true. We had first to do a little twist on it, generalize it a bit, and then to okay, I hope I will have time to that, but it's really getting very technical. Let me say, let me take it for a minute as a black box. And I will say something on connection with codes, and then I will get back to those who will survive and want to suffer. I will show you the cohomological criterion. But let me say something very quickly because I want to challenge you on something. The notion of what exactly Avi is asking, and the real answer is that the connection between the Ramanujan and this topological is via the notion of co-boundary expansion. This co-boundary expansion was defined, not with the name, but essentially was defined using two cohomology, the cohomology over F2, independently by Gromov on one end and by linear Meshulam on the other end. I will tell you, because I'm not sure if I left time to everything, I will tell you here as a story, and then we'll go to the technicalities. I take that there is a notion which is not so simple and very non-intuitive about cohomology over F2, which appear implicitly but independently in the work of linear Meshulam on random simplicial complex, in the work of Gromov on topological expander. So first of all, if you see such a notion which not intuitive, appearing twice by different people, it must be important and natural. And this co-boundary expander, in fact, even its definition found some application to computer science property testing by Tali Kaufman and Mai. We wrote a paper on property testing, and by Irit Binur. What it has to do with this? Because I know that I'm afraid I will use you. I will use many of you when I'll talk about the cohomology. I want to say first kind of a major open problem which is related to all this, and I want to explain why I believe that high-dimensional expanders can be a key to solve this problem. And we few of us are working on that already for 2-3 years. We all the time feel that we are almost there, but so far we haven't managed to prove it. And this is the notion of locally testable code. What is a locally testable code? Locally testable code is a code for which you have a random algorithm, which reads only a bounded number of bits and decide whether a vector is in the code or not, or at least very close to it. That's a problem which of basic importance in coding theory, practically and theoretically. Actually, again, making advertisement to my seminar, next month, in the 13th of January, Irit Dinur will give a talk in my seminar on Wednesdays, exactly on this kind of connection between locally testable code, property testing, and various other things. Anyway, the problem is this is kind of a new direction in coding theory because random graphs do not have this property. You know, in most problems in error correcting codes, it started with Shannon. Shannon proved random are the greatest, they are the best. We try to be as good as random. This is a property that random graphs do not have. This is a property that
random codes.
Random codes, sorry.
And even not, yeah, random codes and not even random LDPC codes.
Right, even not random LDPC, right. LTC, locally testable, are necessarily LDPC, but random LDPC do not satisfy this. Spearman also seems not to satisfy that. Are there such codes? This is still a major open problem. Let me just explain you, just talking philosophy, why I do believe it's not, why I do believe that I-dimensional expanders can help in this direction. Because you see, I want to share with you this intuition that in one-dimensional expander you can also connect expander with property testing. You can show, but you don't read. In one-dimensional graph, you don't read the global structure from the local structure. For example, there exists k-regular graph with large GERT, which are not expander. That's not so difficult to construct. There exists k-regular graph with very large GERT. Sorry, it's not difficult to get that are not expander, but the Ramanujan graph that which constructed by Sarnak and Phillips and me have also very large GERT. So you see, on the other hand, you have k-regular graphs which are with large GERT and are not expander. Namely, we have graph which locally looks very much the same. Both of them looks like trees up to very large radius, and still globally they are very different. The theory, the Garland theory, again, advertisement for tomorrow talk of Isar Oppenheim, the Garland theory is basically the following statement, that if X is a simplicial complex of dimension D, and you need only the following, if you take a codimension 2 cell and you look at its link, the link of a codimension 2 cell is always a graph. If these graphs are expanders, then the complete graph is an I-dimensional expander, not HD, is I-dimensional expander. Namely, the message of Garland theory is that from a local information, local expansion of the links give you global expansion on the expander. So the dream is to do kind of a Sipser-Spielman type of codes instead of doing them on a graph, to do them on, you remember when they did, they call it expander graph. Actually, I think that their names is not so good because they need more than expander. They needed the second eigenvalue is much smaller than k, not just bounded away. But Ramanujan graphs do it for you. And then kind of the dream is to say, let's use Ramanujan complex to get kind of a second floor on of Sipser-Spielman code with the hope that this will be locally testable. So this is just an hope. Another, yeah.
Here, high-dimensional expander, in what sense is high-dimensional expander? In topological, in...
Well, I tell you the truth, the only graph which I really understand are those which are, the only graph which I really understand are those that are the Ramanujan ones. And we work on the Ramanujan one. We try to take the Ramanujan complexes, and we try to build some. We try to build some. Codes on them on the Ramanujan complexes instead of the Ramanujan graphs, with the hope that they will have also the locally testable. We don't have, we haven't succeeded yet. We somehow, I don't know, we go 2 steps ahead and 1 step back, and we are still working on that. Each time we change a little bit the idea. Hopefully we will manage, but I'm not sure. I mean, maybe it's not true, and maybe we are still missing. Maybe it's simply not true. Okay.
Maybe you can say that. I mean, the general idea is that, like in tunnel codes, you choose a local code on the links, and you say that the code on the complex, a word on the complex is a code word if it is satisfied around every vertex. On every link, it is a code word. So it's just the same as in the case of graphs. It's just the hope that
that's the basic idea.
Yeah.
And moreover, you can see that propagating the distance is just as simple as Pima. That's not difficult. There is also a paper of Irit and Parlad, which propagating the local testability is not difficult, but it's not difficult if you have very strong properties of the local code somehow, and that's we don't know yet how to do. We have only kind of we have some thoughts I can share with you, but they are very uncooked at this point. Maybe let me say, even before going to the cohomology, then I will give like 10 minutes crash course on cohomology to those who want to suffer and stay with us. But I want to say something about the randomness, because as I explained before, the random k-dimensional simplices are not the random in that model, the model which was the natural model in some sense, but the model in which Fox, Asaf Naor, Gomo, Laforgue, Janusz Pach, etc., all these people, their model gives geometric expander, but not topological expander. But maybe there are other models. You see, when you say random, it's always depend on what type of model we are talking about. As we saw, these models are not really good, because you see, they give us something. We don't really want to think about a simplicial complex of dimension 2 as something which has only on every edge you have only one triangle, right? It's kind of a silly type of simplicial complex. So we don't really mean when we say K-regular bounded degree simplicial complex that's what we mean. Now there is a model that I work on it with Rui Meshulam, and then with Luria and with Rosenthal, of upper degree random simplicial complex, only upper degree random. And for them, we were able to prove that they are topological expanders. But let's to be honest, this is kind of making it easier for us, because we take the complete graph up to that point, and then we take bounded degree up to the level d-1, and then to okay. Time is running. I just want to say a few words on linear Meshulam, and then we'll rush to the cohomology. Linear Meshulam are set to develop a theory of a random simplicial, higher dimensional simplicial complexes, is trying to imitate, the classical theory of Erdős and Rényi. And but listen carefully what they took. They said they work in their initial work only on two-dimensional, and they say the following: we are taking n vertices, we're taking the complete graph on the n vertices. This is part of the complex, and then we take on every edge, we decide on every triangle with probability P, which is if it's inside or not. And then they proved, just like the kind of the threshold, so what is the basic theorem of Erdős and Rényi on random graphs? They said there is a threshold up to some probability it is not connected, from some probability on it is connected. They wanted to prove it in the higher dimensional, in the two-dimensional case. But of course the graph is connected, the simplicial is connected because they already took the full, the complete graph. It's already connected. But there is the language of homology, or cohomology is a language we can, connectivity means vanishing of H0 of the zero cohomological group. And vanishing of H1 is the kind of the second level of connectivity for two-dimensional objects. They wanted to study the vanishing of the H1. And they prove a beautiful theorem saying that up to some point it does not vanish, and above some point probability it does vanish, exactly the analog to Erdős-Rényi, and then Meshulam and his student Volach generalize it in a beautiful way. It's a beautiful formula for higher dimensional. But their model of random simplicial complex is always, if I look at d-dimensional simplicial complex on n vertices, I take the full D skeleton, and then I take with probability P on every D+1 cell, whether it's in or out. And their model, just like the Erdős and Rényi, is not bounded degree, even not upper bounded degree. And then the work that I did with Rui and then with Luria and Rosenthal, we changed their model to be upper bounded degree, and then we could prove this. But we proved at topological expanded, everything we proved using the cohomology. They proved using the cohomology, using the notion of co-boundary expansion. Gomo proved using this notion. So now I want to spend the last few minutes. It's going to be a little bit technical, but it's only technical, not difficult, just technical. I'm going to give you a lot of linear algebra definitions. That's okay, Avi? Hello?
It's more than okay.
Okay, because
we waited for this.
You waited for that, okay? Okay, so now, but now it's not kind of survey. It's very technical. Okay, let V be a finite set. Let X be a simplicial complex. So this is just a collection of subset of V, so that F is an X, G is in F, then G is also in the collection. For every F in X, we define the dimension of a cell is the size of F minus 1. So it's clear, right? If you have 2 points, then this is an edge. You have 3 points. This is a triangle, dimension 2. Xi, now please follow the notation. Xi is the set, is the family of all faces in the collection of dimension I. And I actually goes from -1 up to D, -1, because the empty set is also part of it, because it's closed under inclusion. And the dimension of the empty set is -1. let Ci now be the family of all I cochains over Fp. What these are? These are simply nothing more than all functions from the I cells to F2. Just put a number on each one of them, 0 or 1. What is the co-boundary map? There is a boundary map, but for our application, what is important is the dual, the co-boundary. The co-boundary map is, you have such a function f. You take delta of f, so delta is a map from Ci, from the I quotient to the I plus 1 quotient. Delta of f applied on a cell f of dimension I plus 1 is a direct sum, is not direct sum, sorry, just a sum of f of g, where g runs over all the codimension 1 faces of f. Right? F is defined on the I cells. Delta F is defined on the I plus 1 cells because X is a simplicial complex. Every face of F is indeed a simplex, is indeed a face of our simplicial complex, and we have it. This is well defined. We define Zi to be the kernel. It's called the cocycle. This is the kernel of delta I. And Bi is the image of delta I minus 1. Both of them are subspaces of Ci. Now, here is an easy exercise. If you never did it in your life, it won't help you that I will do it for you. You have to do it once in your lifetime, not more than once. You have to do this exercise, and then you see that delta after delta is equal to 0. We are lucky here. Everything is much easier that we are in characteristic 2. We don't have to worry about orientation. In the standard cohomology, you have to worry about orientation. This means that Bi is inside opposite. This is a typo here. It should be Zi, right? If delta after delta is 0, it means that the image of what came up from lower dimension is inside the kernel of the next map. So Bi is inside Zi, and Hi is simply the quotient, and this is called the cohomology group of X over F2 over F2. So this is F2 subspaces defined like that. Now, now I'm going to define co-boundary expansion. And this, as I told you, it was defined in a slightly different by linear Meshulam by Gomo, but essentially this is the definition by both of them. And as I said, it's not clear when you look at it first time why, and then you suddenly see, and then not suddenly, I mean, then it takes time to realize that this is an extremely important notion. Let F now be some cell in Hi. We define the weight of F to be the number of top dimensional cells containing it divided by the total number of the d-dimensional cell, and there is a normalization factor here, d plus 1 over I plus 1. Okay, so kind of the importance of a cell is according to the number of edges containing it. If it's very symmetric, then it's much easier to work with, but not always. Even Ramanujan complexes are not so symmetric, so we have to be a bit careful about that. Anyway, if the normalization factor calls you that this is like a probability distribution, namely, if you look the sum of all cells of dimension I, the sum of their weights is equal to 1. So we have, if you want, W is a probability distribution on this cell. And now we define the norm of a cochain, you remember cochain is a real valued function or complex value, real value function on the cell. We define the norm of it. This is going simply to be a real number, rational number really, which simply look at the weight of all the cells on which F is non-trivial, right? F is basically just...
Why did you say real numbers? Aren't we...
Rational, it's a rational number, yeah, sure, rational number.
F are not going to be words in the code, aren't they binary?
No, not at all. Oh, no, F is in the code, I'm sorry. You're right, so F is in the code, but the W is not. W is a rational number.
Of course, but the F is F is just in F.
Okay. I mean the norm of F. F is a binary, right? But the norm of F is a rational number. It's a real number. It's a real positive number or non-negative number, which just take what's the weight, the sum of the weights of F over all F for which F of F is not zero. This zero is zero of the binary field, right? But the weight is going to be a number between 0 to 1, a rational number between 0 to 1.
Yeah, maybe Alex, you want to say that your code assigns a binary value to every phase.
I don't have a code.
Oh, it's not a code. I mean, a function.
A function, right.
You just assign to every phase, maybe every phase of some level, a binary value.
Yeah. And then I take, right, and now I sum the norm of a function is simply the sum of the weights of those phases on which F assign 1, okay? Now we define epsilon I, the following strange things. Epsilon I going to be the minimum over the norm of delta F divided by the norm of the coset of F, where F runs over all cochain in CI which are not co-boundaries. I'm sure if you say them the first time of your life, you don't know, you don't understand what do I want from you. Let me just be formal and give you a definition. What does it mean, the norm of a coset? The norm of a coset, you take such an F. F is, BI is a subspace. You look at the coset F plus BI, and you take the minimum of the norm of G over that coset.
So Alex, you can define it for the, what these mean in the case of a graph.
Right. That's right. That's the next. The next is, but my time is almost over, so I will just go quickly and tell you, you really have to do it by yourself to convince yourself. If you do it, and you do it for yourself, you see that epsilon 0 of x is up to normalization is exactly the Chigger constant, is exactly the expansion. Okay. Moreover, okay, so there is no point that I will do it for you. You really should, if you really want to understand, just do it. Take a piece of paper and write it. I can send you the note, and that's the Chigger constant. So this is, now we think of this epsilon I as the higher dimensional Chigger constant, if you want. So you see, this is another way to say that we are I-dimensional expander, that all these HI are positive. Moreover, it's easy to see that the I cohomology group is 0 if and only if this epsilon I is not 0. It's always a non-negative number, but the cohomology vanishes if and only if it is not zero. Again, that's very, very, very easy to see. And that was the motivation of linear Meshulam. You see, they wanted to prove that H1 is zero, but they wanted something which they can really work with. So they defined this. They didn't normalize and they didn't divide, etc. But basically, that's what they looked for in order to work with something that will enable them to compute what's the probability that you are getting the cohomology to vanish. I'm sorry about this. So that's exactly what they want. For graph, H is connected if and only if H0 is zero. For D minus, for D dimensional, you ask when the D minus 1 cohomology is zero, and then the threshold, they prove the accumulation of the work of linear Meshulam and Wallach is really, truly beautiful, because they prove that the threshold for the vanishing of this cohomology is exactly at P equal D times log n over n. You remember that Erdos-Renyi theorem give you that the threshold is at log n times n in dimension 1. They prove dimension D is exactly D log n over n. It's absolutely beautiful. And exactly in this language, this boundary expansion is the one that Tali Kaufman and I use for this property testing. But now I can tell you the real theorem of Gromov, the technical theorem of Gromov. Gromov proved that if you have a simplicial complex such that all the epsilon I of x are bounded away from zero together, if epsilon I of x is greater than epsilon, greater than zero for every I between 0 up to D minus 1. Nowadays, we call this property up to here, we call it co-boundary expander. Okay. Then X is a topological expander. That's really Gromov theorem, the main. And then he proved that for the complete simplicial complexes, they are co-boundary expander, which was exactly what linear Meshulam proved. That theorem is much easier, and both prove it independently. But the deep theorem of Gromov is that this implies topological expansion. And this is essentially the only method we know up to now to prove a topological expansion. Now, the situation is even more complicated. Ramanujan complexes are not co-boundary expanders, unfortunately. Even if you delete the top. So we had a little technical extension that now we call it cross-historic expander, which is weaker than this property, but I don't want to explain. It's related to the fact that you remember that I told you that for getting topological expanders for graphs, you don't have to have the graph expander. It doesn't even have to be connected. So the problem is that Ramanujan complexes are connected, but they are not I-dimensional connected. In fact, in Ramanujan complexes, the higher cohomology over F2, I stress over F2, can be non-zero. In fact, it is non-zero in many cases. So the epsilons cannot be zero. They cannot be positive. You remember we said that they are positive if and only if the cohomology vanishes. Okay, I probably too fast. But so we have to do more work in order to prove that the Ramanujan are topological expander. Okay, my time is over, and I know people want to go to lunch. Let me just leave you with two open problems besides the one I already mentioned. Okay, are the Ramanujan complexes themselves are topological expanders? This I mentioned already. But by the degree co-boundary expanders, this is still open. We don't know. construction of bounded degree co-boundary expander. Namely, we don't know to have simplicial complexes so that all these epsilon I are positive and they are of bounded degree. Yeah, I think I better stop. It was maybe too much, and especially the last 20 minutes, it was probably kind of torture. Maybe, okay, I will say one more sentence. I cannot overcome the temptation. There is also an open problem to find a good random model which will give topological expander or co-boundary expander. And here I tell you the truth, I wish, I have a feeling that there is no such a random model, but I even don't know how to say mathematically there is no such a random model. What does it mean? There is always a random model, right? You say take all and say put a uniform probability, but somehow there is no construct. I don't know how to say it, but I tell you where is my intuition come from. There is a huge difference in Riemannian geometry between locally symmetric space of low dimension and high dimension. That's exactly what comes up in the work of Mosto and Margulis, rigidity and superrigidity and arithmeticity. Somehow, in Riemann surfaces, you have plenty, and you have a Teichmuller space, which is a space which parameterizes them. If you go to higher dimensional, according to Margulis, you have only a kind of a discrete set. It's a very isolated, and only those which coming from arithmetic exist. Somehow you don't have this freedom, and therefore I have the feeling maybe here also, if you take high dimensional, it's so much more rigid a construction that that maybe there is no random model for that. Okay, I talk too much, and that's really I really should stop.
You talked exactly the right amount of time, Alex. Thanks. So thank you very much. And yeah, questions to Alex, so you can talk some more.
Lior, I see Lior wants to ask something. Yes.
No, I just want to remark that maybe the right way to ask the question is saying that every such a random model will have a singular measure.
Will have what?
A singular measure. So saying the way of saying that you want to, like, you can always have very few points or a very thin set of the stuff that are good, and you can take some uniform measure on them. But saying that you don't have something random in the way that we think of is maybe saying that this is the only case that can happen, and this is like so it can only happen for a singular measure, a measure which is supported only on. I just
I definitely want to talk more about that. I don't know this direction. I even don't know how to what's the meaning of these words.
And
but
another thing
very exciting because I really say I even don't know how to say that. You know what I want to say. It's not like I conjecture something. It's just a feeling that we are not going to get Erdos-Renyi type of theory.
You can just say that there are very few such graphs. This will be a beginning, that the entropy of such a distribution that you generate at random is far smaller than the size of the graph, if you want. I mean, you believe that there are few. You really believe that they come from arithmetic, which is your belief, and you know there are very few of these. This is clear. Right? The number of graphs or the number of simplicial complexes that come from arithmetic relative to the total number of graphs or relative to the total number of complexes is negligible. So
Yeah,
maybe
but
we just want to say that.
But that's too easy. That's not fair. I tell you why. Because you see, most of them.
Wait. Why is it too easy? I mean, if somebody came with a, it seems like a completely far. I guess that's what Leon is suggesting. I mean, you just what is I know you really want to see the arithmetic in there, but what your conjecture implies, that there are very few high-dimensional expanders, right?
No, that's not what bother me. What bother me here is that you see, if you take simplicial complexes, like in the Fox Gomo blah 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 model, you get plenty. Most of them are not interesting. So if you tell me that those which I'm interested is a very few out of them, of course, there are very few out if I count all of them. I need to count within some family which has a reasonable chance, I think, to be. Like, for example, that the degree, look at all those such that the degree of the upper degree is at least 3. You see what I'm saying?
Yeah, I see what you're saying. But anyway, yes, okay. So, we leave the definition of what it means.
I don't have it. I feel that if there will be a good definition, then maybe there will be a good theorem. It's a case which
it happens a lot. Yes.
That's
yeah. Okay. More questions to Alex.
I have a question. Do you have an example of expander, which is a geometrical expander, but not topological expander, but it comes from higher dimensional complex, like expander of dimension, say, of dimension 2, but which comes from dimension 3, because like it kind of makes.
I think that even if you take random dimension 3, so this means that you pick up 4 tuples each time, and then you take and then you throw away and you stay with the 2-dimensional instead of this. I think that this property will still be that the probability that x and y will appear more than once is so small.
But it always appears at least 4 times. So every edge will appear always at least 4 times, right? Because it appears in every.
No. You pick up k. K can be huge but fixed.
Yes.
But I want to be honest with you guys. In all this, when I say bounded, if I really tell you when we put bounded what it means, then you will tell me that these are not really bounded. But we don't have an easy example that that the degree will be 100 or even 1,000. Okay, sorry, but. No, but you see, if you take a random 4-dimensional, say 3-dimensional object, right, which means that you look at the Fox Gomo blah 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 model, you take 4 tuples, random 4 tuples.
Yes. And
then on every edge there, I think you are going to see only 1 triangle.
2, at least 2.
2. Okay, so yeah, 2. Okay, so yeah, 2. So I don't know.
Anyway,
maybe you say let's take random a million dimension and then look at the 2 sub-dimensional. That might be that's a good idea. I see. That might be an idea. Let's look at the dimension. Let's look at at their model of dimension million or zillion, and then look at the 2 skeleton of it. This I haven't thought about it. That's actually might be an interesting idea. Though I have the feeling that no, maybe all right. I don't know. That's a good point. Yeah, that's a good point actually. Okay, I'll be happy to continue to talk about that.
I also would be happy to talk about this more.
Yeah. Okay.
Any more questions to Alex? Or everybody is ready for lunch?
Yeah, I think
Alex may be ready for lunch.
overuse.
So, yeah, we will. Okay, Alex, thanks a lot. So
Yeah. Okay. Avi, you are going to lunch now at the institute?
I'm going to lunch. Yeah, are you coming?
I'll come. I'll join you. I'm in my apartment because I was afraid to do it but I will join you. I'll come.
See you soon.
Okay. See you
Thank
soon.
you all. See you next semester on the seminar at least. Yeah.
Yeah.
Bye.
Bye.